and today I want to introduce my code, and the main structure of my code is just like that. As you can see, this is struct is very similar with class, and we have the string int, name, weight, left and right, and this is actually means like this graph. As you can see, the first one is the root, as you can see, and the root have the pointer. For instance, is 0x0001, and the name is C, and the weight is 5. And if I want to know the left, I have the pointer, which is 0x002. So I can find the 0x002 here, as you can see. And the right hand side is another pointer, like that. I can see that. So this is the main structure, and the next one is a node vector, and this vector I store the node here because in test 1 and in another test we need to know the sum of weight, number of edge, number of vertex, contents, or get leaves, like that. In my opinion, we actually could use recursion to complete this function, but recursion is not effective. The big O of recursion is bad, so I use a vector. As you can see, I use a vector to do these things, and I think it's more effective. One is the add vertex function, and in add vertex function, I write another function, which is the insert, and I add the weight and the name here, and I also input the root. So this actually means if the root is null, I add the node. I create a new node, and the weight, and I set the weight, set the name, and the left and right is null, and also add new node in node vector. And if it's bigger, if it's smaller, I go to the left hand side and the left hand side and the left hand side, and it's a recursion, as you can see here, recursion. And if it's bigger, I'll go to the right hand side, right hand side, right hand side, and it's also the recursion. For instance, I want to add 15 in this visualized binary search tree, and I will find is 9 now, and this root function is not null, it's 9. So if I want to add 15, first it's not null, and I say is it big, the 15 bigger than 9, and actually 15 is bigger than 9, and move to 12, and 15 is also bigger than 12, and we move to 14, and 15 is also bigger than 14. So it's actually recursion, and the left and the right right and the left and right node of 14 is null, so I add the function here, and 15 is bigger than 14, so I add the right hand side. As you can see, the visualized is just like that. It's pre-order, in order, and post order, Actually, this 3 is not hard. As you can see, it's very similar, and the difference between them is the uh, is in pre-order we add the name before the recursion, as you can see, and in order vector in order we add the name between recursion, and post order we add the name after recursion. So it's like that. One is number of vertex, and in this one I use recursion, and it's just like the recursion is like that. The first one is 9, and the left hand side is 8, and the 8 don't have any now, so we save the 8 firstly, and we back to 9 and write down the 9, and it's in order, and then we go to the 12, and the 12 have the left and have the right, so we go to the left, and it's 11, and 11 don't have any left and right, which is now, so we write down the 11, then 12, and then 12 go to the right hand side, which is 14, and 14 don't have the left hand side, so we write down the 14, then we go to the 15, and 15 don't have any left and right, so we write down the 15. It's a recursion like that, and in recursion we can got every vertex, so we use count plus plus to know the number of vertex, and the next one is sum of weight. I also use recursion, and every recursion we got the weight, and we add all. And the next one is exist. In this function, I use a node vector. I think node vector have better performance, but it also occupy more space. And as you can see, we got a vector to store all the node, and if the name equal to the name that I input, so I return true, else I return false. And the next one is get all vertex, like that. And this actually, I store all the vertex in this vector, as you can see. And the next one is got all leaves. Leaves actually means I don't have any child, which means left and right is null. So if left and right is null, I push back and I return the leaves. And the next one is neighbor. Is neighbor. So I also use the node vector. For instance, I check did them have left and right, and the left and right is left and right. For instance, is 8 and 9. I check 8 is 8 have left and right or no, and 9 have left and right, and 1 is 8, 1 is 12, and I check 8 is right leaves, right of 9, so their neighbor, so it's like that, you can see. And the next one is Okay, then we go to the remove vertex function, and in this function, firstly we got the current weight, and we add the current weight in delete vertex function, and as you can see in this function, I can delete this function, and this kind of code actually means I move to the vertex that I need to delete, and this kind of code actually just actually means a different decision. For instance, if I want to delete the leaf, it's very easy because leaf don't have the left and the right, so just delete it. But if I want to delete like 14, it's pretty complex because I need change the uh, left and right of 9. For instance, if I delete the 14 and it changed to 15, so I need to change the 9. So and I also